Hey everyone, welcome to another Common Lisp study group. I'm your host Ram Vedam with Atlanta Functional Programming. Today we're going to be discussing and continuing our discussion of the deep dive of type system that Common Lisp provides. Last week we covered kind of a brief overview of the type system, how to explore types in the REPL using typeof, briefly described how to declare types, specifically fixed types inside the built-in types that are already available in Common Lisp inside functions using things like declare. When you're inside the REPL, you might be trying to fixate a particular return value of a form. We could fixate that return type using the operator. And additionally, we kind of introduced the locally form for cases where you want to further restrict declarations. We're going to continue some of that declaration exploration today. I'm going to give a little bit more of a deep dive what declare, declaim, proclaim kind of fit into in terms of the entire Common Lisp system in types specifically. Additionally, last week we covered things like basic type specialization, especially in the context of arrays. And before we ended, we talked about declaring simple types using the deftype keyword. We're going to continue that discussion today, along with going into more of a deep dive of the type predicates, subtype and subtype P. We talked a little bit about that last week, about what their differences are, and kind of when to use them and when not to use them. Additionally, we'll talk about today what is the difference between, say, type of versus class of, along with using declaim more for top-level checks, which we introduced last week kind of in the discussion, but we never really gave an example. And we'll talk about today, additionally, the runtime type checking facilities that are available for you. We talked about two of those, type P and subtype P, are available, but there's an additional one called CheckType, and we'll talk about that too. And finally, we're going to go through some of the type dispatching mechanisms that are available at your disposal in the form of type case, E-type case, and C-type case. So let's begin. Last week when we kind of ended, we were talking about the deftype keyword. This keyword, if you recall, basically gives you the ability to create custom types. Now, I'm going to say first and foremost that deftype is more of an aliasing mechanism. It allows you to create essentially the predicates that are used with the type checking facilities, especially the runtime type checking facilities, in the form of CheckType, type P, and subtype P. Additionally, once you've deftyped something, you ultimately can use that custom restricted type inside your declarations as well. We didn't go through that last week. We were going more in what's available in the built-in types, but you could certainly see in our example here with our add function where you could certainly use a declare here instead of, actually, let me move this guy. If we had our type defined before our type function, we could certainly add a declare here and say and number AB, and this will ultimately also work. You could see that this ultimately restricts the inputs that are allowed to come into, say, add. So now when we go in and add, 1 and 2, it'll work perfectly all right. But if we add 11 and 1, it should throw an error, because error is not of type. It's not a hand number. Now notice the kind of error that's coming here. This error basically says that it's not mod 11 binding A. Really, that's happening behind the scenes is hand numbers being converted into what it is, it's an alias for an integer between 0 and 10, recognizing that the upper bound that's exclusive is 11. The compiler converted that into essentially a group of mod 11, and it through that as being the type ultimately inside the binding when it was trying to bind the variable a. Small subtle difference, but it could throw off beginners, and it makes sense given what hand number is. All right, in this example, we are talking about a simple type alias to an earlier type that we provided a restriction to. Now, there are ways of using deftype to make more complex type. This is a very simple example that we came up with. All right, this one is something where the type information is a hint to the compiler saying that we're restricting a built-in type available to us, and we want to essentially restrict those inputs that are going into this function to this particular restricted type. But can we make a more complex version of this type predicate? Yes. So the way you do this is you first do two things, okay? And a good reference for this for folks who are looking into this is the documentation on deftype itself has an example where it's dealing with the matrix case in the hyperspec. But additionally, the Common Lisp cookbook has a fairly decent example on creating a complex type too as well. Using deftype that is, and I will go through that a little bit. We're going to do a bit of a deep dive on that example. In that example, and I'm going to go ahead and put this reference from the Common Lisp study cookbook. This example, and it's going to be slightly adjusted for, because I feel that the explanation and the code went in two different directions. But the idea is let's say that we want to create a type that essentially is like a fixed array of 10 integers, right? So you're only looking at that the array it holds an integer. Every element in the array is an integer, and the array size is 10, all right? So how would we do this? Well, we first create what's called the predicate to essentially which essentially takes in the thing that we're trying to restrict on, and it will at the same time it will do some checks against this thing. All right. So now, what exactly is this going to be? Well, it's a basic predicate, so we know what we want it to do. First, we want to know that the type of the thing is an array. Array P is already available for you in the in Common Lisp, in standard Common Lisp, for folks who are not aware. Additionally, we want to know that this is a fixed size of 10. So that means anything less than 10, anything greater than 10 are invalid. It has to be just 10 integers. Well, we could do that by just saying the length of our thing is going to be 10. All right, we have that now. We have that this is going to be a fixed array of 10 things, right? Additionally, we want to make sure that every element in the array is of type integer, all right? And the way we would do that is we have every is like all, std all in C++, and many other languages have this kind of basic shortcutting thing that instead of writing an iterator to go through every number in there and checking it. And what we're going to do is this every guy is going to take in a predicate. Well, we have a predicate built into Common Lisp called integer. So we're going to say that everything is an integer, all right? This is our basic check, all right? But this does not actually define the type, all right? this is just a check that we're going to use to pass into the def type to create the actual predicate that's going to be used by type P. All right. So the way we would then use this is we create our array of tenants, which is our type. We'll take an optional of the type that's actually being fixated in there. All right. And what we'll do is we'll check to make sure that it is an array of this type. And I just forgot one thing. Just to review, def type itself is actually going to be passed into a macro. All right. So you'd have to actually make sure that it's quasi-quoted. The predicate is quasi-quoted so that it appropriately gets injected into the larger predicate that's the predicate generator that's actually being created by type P, so that the actual check can actually run accordingly. Otherwise, you're going to get some weird errors. And once we've done this, the final thing is obviously calling our array of tenants P on our actual thing, but we're not actually passing. Notice in this type specifier, we're not actually passing the instance that we're doing the type check against. That's happening later on when we actually invoke this on some sort of instance number, right? So what you can do is you could just simply call satisfies, all right? Now, you might be thinking, well, since we've already passed in, so I'm just going to show this to you first. So this is the type signature of this, all right? And we can see that this will work if we just simply call, type P on a vector, let's say 6, 7, 8, 9, 0, and we call array of tenants. Okay. If this obviously was changed to less than 10 integers, it won't work, obviously. Now, an astute reader will look at this code and say, hey, Ram, you're not actually using the optional type. Do you really need to pass in the optional type into the signature? Well, no, you don't actually have to do it in this case, right? We can actually clean this up a little bit and get rid of all of this code here and make our thing simple. There. That's what I was looking for. All right. And this will still work. All right. You can see that we can actually pass in the thing. The main thing to take away from this, though, is when you're creating predicates of more complex types, all right, creating a function and then passing it into satisfies is the way you would end up creating the type itself so that it gets registered into the type system. The satisfies keyword is not actually a function. It's actually a macro that takes in this predicate and internalizes it in such a way that when you call it the type in type P and subtype P, it gets invoked accordingly with the standard Common Lisp machinery. Unfortunately, I tried macro expanding this guy once, but it doesn't actually seem to expand unless it's in a much larger macro invocation. So for folks who are aware of how to dig deeper into satisfies, let me know, because I'm kind of curious how some of that machinery pieces work. But I'm letting you know that if you're creating predicates for complex types, this is the way that you would register these types into the Common Lisp REPL. Are there questions about this? go look into. Okay, cool. So deftype, like I said, creates essentially type predicates that are going to be used to register, that can be used inside of type P and subtype P to register hooks that can be used for type checking when you're especially writing code. Now, deftype, again, though, is not the only way of declaring types inside of the Common Lisp type system, right? We've actually seen many ways of actually creating types inside the Common Lisp type system. Defstruct creates a type inside the Common Lisp type system, as does defclass. But in addition to these two, there's also one that we've talked about when we were going through practical Common Lisp, but it is kind of its own topic, and that is conditions. So you can actually define a condition object, and its object hierarchy is separate from the rest of the object hierarchy. At the end of the day, it's disjoint from def classes, which creates user-defined classes, def structs, and def types. These are all what's called, I think, according to the hyperspec, pairwise disjoint specs, but they all, at the end of the day, point up to T, which is the root of the entire object hierarchy. Now, one thing that's particularly interesting about this is because these guys are all inherited from T, you can actually determine whether or not something got returned to a particular type or got promoted. So last week I kind of fibbed, but it wasn't really a fib because I wanted to kind of introduce this when we were going through all the different types that are different ways of creating types, and that was we didn't have time last week to go through it. But when I said that when you were looking at the operator and you wanted to check to see if you were, let's go back to the example to actually really bring this home. So last week we created something like this, and I said that there's no way of knowing that this is a fixed num unless you go look up whether or not that's a fixed num. And we talked about that the upper bound of this guy is actually just most positive integer. If we do integer length of most positive fixed num, it is essentially the most positive fixed num. Okay, it's a 62-bit integer. But you really want to know whether or not this is a fixed num type or is an instance of a fixed num. Now, because Common Lisp type systems are essentially instances of objects, right? Instead of using type of, which gives you what the actual type is, and this is the correct actual type, it's the ranges of the type, what are the valid ranges of the type, what are the valid values of it. If you want to see if something is of a fixed num type, which is a class built in for a built-in type, you could just use class of, and you'll recognize that this is actually a fixed num type, right? A fixed num instance, right? The differences between type of and class of is something to be aware of. Type of basically gives you the actual type information as defined by the type built into the def type predicate. All right. Class of, though, it actually gives you the instance, in the implementation instance, details of the actual object constructed. All right. So the cookbook actually has a great way of saying this. It returns the type of a given object in the type specifier format. So type of gives you the type of a given object in a type specifier format, which we've talked about. This type specifier format is essentially the ranges that are going to be used by satisfies, essentially, for complex types, or if you're using a restricted type version of an existing built-in type, you would be able to use just the type name and then whatever range restrictions that this type can be put on. All right. Class of, on the other hand, gives you instance details. All right. And what's nice about this is you can also use this combination when you're especially doing prototyping. I'm not suggesting you do this while you're writing production code. When you're prototyping, you go verify this, and then at some point, if you're trying to, restrict your API or whatever, you can add declare identifiers using declaim and stuff to actually restrict your API in such a way that you can essentially provide some compile time checks and at the same time provide some performance guarantees. But the reason why you can use this in prototyping is you can then check to see if certain calculations, for example, do automatic promotion for you. I'm going to give you an example of this. So I think I was doing this morning, so hopefully this will work. Let's say that we are doing fixed num, and we do minus, let's do most positive fixed num minus 1. Okay. So when we're doing some sort of calculation between, some sort of number, think of this subtraction just being any function call against some input that is of a fixed num type, okay, that returns a fixed num type. You could see based on the calculation that if I just simply change this to a different operation, and let's say that we change the implementation internally, pretend that this is a implementation detail that's internalizing inside a function, okay, that you're using DA to restrict the type that it's going to go into. If you use class of and see what's actually being returned, you'll see that it'll throw up an error that that's interesting. Right. So, but if we change this to an integer, you will see that it'll stay a fixed num type, but if we just simply change the implementation detail, it'll automatically do type promotion and change it to another big num. So two things can be taken away from this. The DA operator gives you the ability to know if you know that you want to keep a particular value within a particular range or a particular construction and a hierarchy. It will show you that in what cases you may want to go lenient and actually use a more general parent class of that type hierarchy to allow type promotions between the different type hierarchies. And again, for folks who aren't aware of how it's usually a linear type promotion, it'll figure out based on size restrictions in the type hierarchy to determine the best class format to actually go and instantiate the object behind the scenes. But this is what allows the flexibility in Common Lisp to go through the different types, especially integer types and floating point, fixed point types, where it allows you to actually promote a particular calculation between different object instances. If you restrict it the way that I did earlier with fixed num, you saw that it will tell you that, okay, you're doing something wrong here. Your implementation used to work, and now it's the type that you're restricting on no longer is valid. You need to either go in and change it, make it more general, or go and change your code to actually go and correct things. Does that make sense for folks? Let me see if there are questions here. Yeah. I hope I answered my question earlier about, okay, so and the question is if we require an array of ints, type has an optional type parameter. Yes, I actually, I hope that my cleanup answers that question. regarding why pass an optional type parameter. Sometimes you may want to pass in an optional type parameter. You don't need it, is kind of what I was trying to illustrate there. The optional type parameter provides you some way of actually creating generalized type specifiers that can be used to give you some way of doing some sort of type checking at the runtime. Okay. Take a look at the live stream. Questions? No. All right. Cool. All right. So let's move on to. So we briefly discussed last week about declare, declaim, proclaim. These are all what are called declaration identifiers, okay? Now, I kind of, breezed through that last week when we were trying to get, just some of the type definitions into a function and kind of show you some of the stuff that especially SBCL provides you when you are actually restricting the types and how that actually affects code generation especially. But I wanted to spend a little bit of time talking about these declaration identifiers a little bit more in detail, just to give you guys a heads up that it helps not only with type correctness, but also helps in also hinting at the compiler and ways to optimize. Okay, so for folks who want to dig deeper into this, first I'm just going to mention what hyperspec section it is. It is section 3 on declaration identifiers that I'm essentially introducing here. For folks who haven't seen these declaration identifiers, I encourage you to go look at section 3, just because it is a kind of an interesting overview of what is actually available for you to do in terms of hinting to the compiler, hey, do something this way, all right? And I think that's pretty cool for folks who especially want to have a little bit more control over how certain things are going to get optimized and how certain things are going to get introduced in terms of the compilation pipeline and how it affects code generation, all right? So a couple things that I'm going to mention first, and these are just some brief definitions because it's kind of important when you know the difference between, especially when we go through some of these examples, what are we looking at, right? So a declaration identifier and a declaration form, essentially, are processed by the evaluator or the compiler and take them as hints to actually go and do code generation, right? Probably, in like SBCL especially, it's going to be usually hints to ultimately hook into the machine code generation to generate native assembly instructions. As you saw last week, we have used local declarations when we're talking about declare. So when to go back to our example here, when we use this declare, this is called a local declaration because the scope in which these type hints are actually going to be alive in are within the scope of the actual function call, right? The function definition itself, right? Global declarations are stuff that we kind of hinted at when we were talking about inlining the add function here, as you see in line 4, but we didn't really, I didn't bring up what this inlining is and things, but these are what are called global declarations, right? The DOF special form essentially is a local declaration, but it is restricted to a specific form that you're actually invoking within the scope of that DOF, right? So these are kind of some scope rules that you need to be aware of when you're dealing with these declarations. Now, the declaration specifiers themselves, and this is kind of like what inline is, what I'm going to be introducing later on with ftype. These are essentially expressions that are only valid inside of a declare expression or a declaim expression. Basically, the first argument is the identifier that tells the evaluator or compiler what it is that you want to do. And there are many pre-built, some built-in identifiers that are specified in the Common Lisp specification, specifically if you look at section 3.3.3. And there's only about let's see, I think I'm looking at about 10 of them that are related to actually providing hints. But some of these hints are very, very useful in terms of providing restrictions if you know what you're doing, especially for the advanced Common Lisper. This is particularly useful because they could say, I'm telling you this is what you need to do, and the compiler will use those rules to act accordingly, which gives you a little bit more control over the compilation process. And I'm talking about features anywhere from what we're going to be talking about in terms of ftype and type, in terms of which are essentially restrictions on type declarations versus the things like whether or not we're inlining or not inlining. You can there's actually a declaration that essentially allows you to say that, hey, within the scope of this function, or if you're doing it at the global level, although I encourage you not to do this, make this function not inline, so that behind the scenes the compiler will go, okay, I need to make this an explicit function call, and it'll do whatever it needs to do for the machine architecture to go and make sure that's a valid function call and it gets returned. But there's also other declaration specifiers that I wanted to at least briefly mention here, just so that you guys can take a look at this, because I think it's really interesting as to how it works in terms of the compilation process and how much control it actually gives you. So we talked about, so there's things like ignoring arguments. We've seen that before. There's a way to actually provide the compiler hints that a variable can be stack allocated, which is pretty neat, and that's in the form of a dynamic extent declaration. The dynamic extent declaration, I was trying to come up with an example of this that would be best to illustrate it. The one example that it provides is dealing with lists, but I haven't actually, I'll be honest with you, I haven't actually tried out what's in the hyperspec in terms of declaring something dynamically extended and see what actually occurs at the assembly level. So, but I'm going to briefly mention it here so that you guys can do some experimentation. If you come up with some particularly interesting examples, let me know. Within the context of today's discussion, though, in terms of types, there are two specific declarations, expressions that I think need to be brought up. One is something that we've kind of used in a sense, but it's not actually it's not the way that, there's another way of actually declaring something, all right? Declaring it this way, all right? So these are functionally equivalent, all right? And that is the type declaration specifier. So you see how we have this declare with the hand number here. This guy is actually a shorthand for a much larger thing. Specifically, this is actually a shorthand for, and let me just comment this out, declare type hand number, which is our type specifier, and the arguments. All right. What this is doing is this essentially takes in the type specifier format, which is, again, like I said before, is nothing more than a macro here, to some sort of predicate, and it will take in the rest of the arguments. And behind the scenes, this type specifier will actually take this and register it accordingly to the type system, right? This shorthand, essentially, this hand number, instead of writing it this way, if you wrote it this way, this shorthand essentially expands into this and then ultimately compiles the same code. So it's the same damn expression, right? I don't think, based on my reading of the hyperspec, I don't think there is a preference. I prefer, I think, the shorthand versus this type hand specifier, but there might be a situation where this longer declaration might be more useful. I haven't seen one, and I haven't hit a case where I needed to explicitly do it this way. The other one that we didn't really talk about, but I hinted at that there is a way of doing this, is providing essentially a declaration specifier for your functions. At the top level, you could also do this at the bottom in a local declare. Specifically, if you're using, like, say, labels, that might be at the point where you might want to do like a locally and then declare the labels, that is, those inner functions that you've created with labels or flet, has being these function signatures, if and when your profiler tells you that they're potentially bottlenecks. But at the global level, when you're using declaim, you can also do this, and it's the same specifier. It's called ftype, all right? What ftype provides is you to essentially write what looks like a proper function signature that you would see in, say, any other programming language. Now, obviously, there are better shorthands in other languages, like, say, Haskell or OCaml or ML variants, where you essentially provide the function name, colon, the arguments. But this is actually a good way of documenting your function signatures. And if you know that your function only takes inputs of a particular type and outputs of a particular type, you may as well go ahead and use ftype to go and restrict it. So that way you could get some type information and type checks at both runtime and compile time. Now, the format is fairly straightforward. You specify ftype, which is your function signature. And if I recall, ftype does the same thing that fixnum does and all the other type specifiers, in that you could provide multiple function signatures. I just did it this way for illustrative purposes. But you could essentially start with, hold on a second, yeah. Right. So what this thing does is it takes in a function, and you have to specify each function like this. And that is, you don't specify the name of the function and then its arguments. Instead, what you say is ftype, I'm specifying a function, and it goes through here, which is a set of inputs, and it returns an output. Now, this is for folks who are coming in from languages that have what C++ is now calling trailing return syntax. This is essentially trailing return syntax. You would see the return type of the function usually at the end of the function signature. I think a lot of languages have now adopted this signature syntax. So I hope it doesn't cause confusion. After you specified the function signature, what's beauty about this is this signature essentially can be used to restrict the signature for one or more functions. So you can actually list all the function names after this function signature that have the same function signature, essentially. So, like, if you have, say, subtract, molt, and div, or something like this, where each of them essentially take 2 arguments and return an integer, it will go ahead and restrict them at runtime and restrict them at compile time to saying that they can only take in integers and return integers. Okay. Another example of this is obviously here. This is not just restricted to built-in types of integer, signal, float, double, and stuff. It can also be used for restricting types using unsigned byte, which allows you to essentially define like 64-bit signatures if you need to. Personally, if you're going to be going through that, it might be appropriate too. to go ahead and make, say, like a type alias or something, and then put a global declaim just to name some of those types for restrictive purposes. But this is just letting you know this is another thing that you can do. And this is not restrictive to just primitive types. This is also allows you to write function signatures for even complex types using, say, like def struct, def class, and so on. Right. Point is when you're providing your API and defining your API, especially using a declaim, actually does make some sense. Just because if you already know what signatures and inputs are provided, why not just go ahead and do that? So let me try something here. Okay, so I was mistaken on this. Because this is a REST argument, this would not work. But essentially, what I said earlier about ftype, ftype essentially allows you to start with the signature and provide, as a REST argument, all the function names. You can't provide multiple function signatures in the same ftype precisely because of the fact that you can list one or more functions at the end of a function signature declaration to determine what functions are of this particular function signature, right? So for each different function signature, you're going to have a new ftype. But for every function that has the same function signature, you don't have to declare ftype. Instead, you can just add it to this list, all right? And it'll get restricted at runtime and compile time. Does that make sense for folks? All right. So up until now, I've been using type P and subtype P a bit willy-nilly, but I'm going to start, encapsulating them, saying what are these type predicates really for? So type P and subtype P fall under the category of runtime type checking facilities for Common Lisp. It is something that is normally done. Oh, okay, there's a question. Makes sense. Other than readability, make a difference. So we have a question here. Other than readability, does it make a difference whether you have a single ftype with multiple functions versus one ftype per function? That's a good question. I would say one ftype per function would not make, especially if they're all the same function signature, will make much sense, just because at the end of the day, I would say that they would collapse to the same sort of declaim with a single function type, and you're just cluttering at that point the code, because they're all the same, right? Why not just go and say, okay, these function names all have the same function signature, so we're just going to go ahead and restrict that. So I would say that the readability argument is really a big difference, though, right? Versus having one ftype per function. Now, that being said, if you have distinct functions, you saw what ftype has. Ftype's function signature essentially takes all your function names as a REST argument. So with REST is not an associative list. It's just it treats every argument past that REST keyword has an element in a larger list. So it doesn't do any sort of parsing. So if you try to add two different function signatures under the same ftype, it's going to cause an error, because it's going to treat that entire parenthesized thing as a function name, not actually as a separate function signature there. Does that make sense? Oh, okay. All right. So, as I was saying, the runtime type checking facilities inside Common Lisp are fairly extensive and it includes these type P and subtype P predicates. So that means when I'm saying runtime type checking is again, this is a REPL, this is a dynamic language with an interactive programming environment. So that means when you're instantiating things or running things at the REPL, using type P and subtype P makes sense. As well as if you're actually doing type checking inside, say, a function, you could use type P and subtype P as well. So if we want to say, instead of doing what we did here, which is declare, and this falls under compile time type checking facilities. Declare, declaim, and proclaim are all compile time type checking facilities. If you wanted to just do this check at runtime, instead of actually doing a declaration, there's a couple of ways of doing this. One is we can use an assert type P a hand number, and then we can also do assert type P b hand number, and this essentially at runtime checks that A and B are of the same type. If we pass in 1.5 to 2, you will see that A is not of type integer with the binding at the runtime type check. And this goes the same thing with subtype P. But instead of doing this, you also have another thing, which is a macro called CheckType for runtime type checking. So CheckType, let's try this with, instead of doing this, assert, let's say that we want to CheckType A with our hand number. Okay. CheckType A, hold on. This is wrong. Hold on, let me just mess this up. I think I messed up this guy. Yeah, there you go. Much better. Prevents use of assertion from type back. Let's see what this is complaining about. Yeah, that's because of the fact that I restricted this earlier. So instead of playing around with this guy, because I just did a declaration on this, I'm going to make a separate function called myAdd, just to make things a little bit easier. All right, shift down. We're going to create the same myAdd example. This goes to show you, you don't want to mix type checking facilities as you're playing around with things. You'll get some of these interesting warning messages. Okay, so we had essentially B as being an assertion, and what we were trying to do is essentially use CheckType A and number. Don't believe I need to specify this as a quote, so let's do that. And undefined. Oh, sorry. This happens. Oops. Here we go. Right. Much better. All right. When we expand CheckType, what CheckType does is essentially what we did before anyway. It actually creates essentially a do form, and if that do form gets an invalid predicate, it will throw up an error saying that this is not of this particular type. Now, a lot of this stuff that you're going to see here is SBCL specific. So the error and the macro expansion of CheckType is implementation defined. You're going to have to actually go look at your implementation specifically to see what's going to actually happen there in order for you to determine whether or not it would be better off doing one thing versus the other. All right. Personally, these are functionally equivalent. So if we do this, you can see behind the scenes, it's essentially the function call is on asserts error instead of a do type error that you saw earlier, a CheckType error. So when we run this again, you'll see again that everything works fine if you pass in the correct types, but if you pass in incorrect types, you get a throw in saying that the value of A is 1.5, which is not a type hand number. So CheckType at runtime gives you some pretty nice error handling and some nice, as you saw here, this is a pretty clean error message in terms of what you're doing. But as with anything that occurs at runtime, there's a cost to it. If you compile this, and it has to keep that CheckType especially, you're going to incur some costs in terms of compilation and in terms of actual performance evaluation. So use CheckType and assert type P very, very carefully, and profile your code to make sure that they don't end up causing bottlenecks, especially if you end up using a code that does runtime type checking in, say, like a loop or something like that, because that could actually slow down the performance of your code. We talked about compile time type checking. Yes. Now we're hitting a very interesting thing. So we covered a good portion of our overview of the type system in Common Lisp, but there's one thing that's particularly interesting to me, at least, and that is there might be cases where you want to actually dispatch based on the particular type that's being passed into a function, okay? Or even just perform some sort of action at runtime based on the type information of the input that's being passed in. Again, because this is a dynamically typed language with some type information that you can look at, there are some facilities to allow you to use this to your advantage and create some generalized algorithms that allow you to provide specific things for specific types that are coming of inputs that are coming into that function call. One of these facilities, and the main facility from what I can tell inside Common Lisp to do this, is type case. All right. So for folks coming in from other languages, type case and type dispatching is a lot like like the type switches that you would see in like languages like Go, where you actually go and look at the input value of the type, which behind the scenes, what it's ultimately doing is looking at the tag implementation inside the structure that it provides in the Go system, and then use that information to go and dispatch on that particular type to either a function call, or if you want to do some sort of action that will end up executing some set of forms based on the type information that you have. All right, this is an actual different mechanism for doing different actions based on type information than what CLOS provides. CLOS does multi-method dispatch, as everybody knows. We're using def method and def generic and that machinery and hierarchy. But it's a separate mechanism in that its dispatching mechanism is entirely based on the type information that are in the type specifiers that you provide. All right. A good example of how one might use this is, say, writing, like, say, a generic, let's say you want to create a generic plus operator, right? So you might say generic add rest args. All right, and what you could do is use essentially the type case situation to actually go in and based on the type information, go and either call the plus argument directly or do something else. Now, I'm going to write this as a last example, but because I think to really introduce this, we're gonna start with something even simpler. Let's say that we're just trying to write a increment number operation, right? Because I want to first introduce to you guys the three types of type cases that are available inside Common Lisp first, before we go in to the generic operation as to the real good application of this. But in the simple case of an increment operation, is you're taking an argument. If it's an integer or a float, you want to there are some nice shorthands for actually incrementing integers and things and floats versus everything else. If it's not a number, then just go ahead and throw an error. All right. So in this case, what you would do is you start with the type form, and type case looks ultimately like a cond almost, in that there are different cases for each ones, and there is an otherwise clause that you can actually provide, which is usually T for all other types that compile down into T. So in this case, the cases are specified by type name and form to interact on that type name. So we might have, say, integer call 1 plus. If it's of type float, we might end up calling arg plus 1, all right, which is the generic plus operator there that can take in any type. And otherwise, if a is not an integer or a is not a number of anything, we just go ahead and throw up an error. Sorry, I have to first type in error, format string. It's not a number. And then we specify the arguments. All right. So now you can see here with this function, if I specify 1, everything is good. If I specify 1.5, again, everything is good. But if I try and say increment number on h, it'll go and throw an error saying h is not a number. Pretty cool, right? But let's say that you have some code and you want to recover from the error based on the type information that's coming in, saying that, oh, I accidentally passed in a type character, but what I really want to do is pass in a different float. All right. Not saying that this will ever happen in the case of this contrived example, but there are cases where you might end up having something similar. Right. In that case, instead of using type case, all right, and I'm going to go ahead and I'm just going to paste this and check this guy in so folks can actually take a look at this on GitHub if folks are interested. So in this case, you would use something called CType case. CType case is basically a type case that allows you to recover from a particular error that's occurring. Right? And what it does is it specifically provides a built-in condition that allows you to change at runtime the value that's being executed. Okay, and it'll look like as if no error ever occurred. This is one of the beauties of the Common Lisp condition system, as most of you who are listening in on may have read. This condition system allows you to stop the stack at the point where the error occurred and allows you to go and change the state of the stack, the state of the frame to correct it, and then later on continue execution. And this really drives this point home. So if we use CType case, all right, and we run, actually, let me go ahead and rename this guy here, C dash increment. Recovered. Let me call it that way. Okay. We call this guy here on our incorrect input. You will see. A second. I messed that up. No, I thought so. Let me just recompile this guy. That's not doing what I expected to do. Oh, my apologies. I'm being dumb here. One thing about CType case that it's because I provided an otherwise clause that this is not working. It's actually reverting to type case in this case. And if you actually look at the code here, it recognizes that it generated this as its own case, which means it's actually not going into this and it's not setting up the condition system. So let me delete this guy. All right. Let me go and look into this. And when we cover the three, I'll go ahead and do a macro expansion so that you can see the differences again. But first, CType case. If we run this guy, this is what's been supposed to be. It says that the input that we passed in does not fall into any of the valid cases. We wanted one of either an integer or float. Obviously, a character is neither of those. So what do we want to do? Well, if you look at the restarts there, the first restart is the one that we wanted to actually go in and talk about, which is store value. And what that is doing is we stopped execution at the point where we're supposed to actually do some sort of dispatch. Okay, and what we're doing is the CType case actually injected a new condition saying, okay, here I have a handler here that allows you to go and restart the computation with a new value. So if I hit 0 here, if you look at my mini buffer, and I apologize, I can't seem to actually go in and increase the size of my mini buffer. Well, what it says is, oh, nice. It looks like I just did. I just had to do the wrong thing. Let me do this one more time. Okay. And let me do this one more time. Plus adjustment. There we go. I hope folks can see this. It's large enough. You can see that when we hit 0 for store value, it'll throw up an input prompt saying, okay, what do you want it to actually be? So now we can actually go and change this value, and it will just continue computation, and we re-execute the function. Okay? It will go ahead and restart the function using the restart function restart that's been built into the CType case, and it will go ahead and run through those cases again and figure out if there's a valid input in there. And it's as if we never got the error, which is kind of nice. If you have an unrecoverable error, though, okay, saying that, like what I wrote earlier, which is the type case, you don't need to necessarily write this particular input. What you can do is just simply take this guy and simply change C to E. And what this does is it essentially does this sort of expansion that I just showed you. Let's see how this works. We compile this and we run. Oops. Boom. You'll see what we saw before. Instead, what happens is it goes through an E-type case expression. It says that it's wanting one or the other, one integer or a float. Again, character doesn't fall in any of these, and it'll just either allow you to retry or abort. And that's essentially what my type case example kind of expanded into. Now, each of these type case, C type case, E type case are macros. If you see what the macro expansion does in type case, it's pretty simple. It converts it into a cond. That's it. That's why, and what it really does is specifically is, and this is what you should pay attention to, it takes the gensim of the argument and it checks its type using type P. So if you end up writing code at some point that looks like you're doing cond type p blah blah blah, that means that you should really go ahead and refactor that to use a type case, just because it's you shouldn't be writing you're cluttering up the type checking, and it really does not provide you any benefit from writing it that way versus just writing straight up a type case. Whereas with C type case, when it expands it, this is what we ultimately get. This is the actual thing that we should see. Again, this generates into a tag body with a tag, okay? And the reason why it becomes a tag is because this restart, what it does is when we get the store value, it actually just does a jump point, and then it goes through the case again, all right? Which allows you to have infinite restarts and try different values every time if you really wanted to, although that's really kind of dumb. And the main thing that you should see here is SB kernel has this, at least this built-in case body error guide that actually converts itself to, I don't think this is, yeah, this is just a function call, that provides a restart behind the scenes that will give you that store value restart that you can then use. And it will return from this function with that new value, set it to the argument again, and then run through the, go back, restart the computation by doing a jump again. All this code is generated for you guys. You don't need to really, create it all for yourself. That's the beauty of some of the macros. So I think it's important that you look into that. Finally, E-type case. E-type case, no difference. Only from the it's no difference from what I originally wrote with type case, but there is one small little thing that you should be aware of, and that is just this, which is E-type case failure. If you're writing code, especially like on line 39, where you're saying this in a type case, that really means that you want an E-type case failure, because it will generate a very meaningful error message for folks, especially who are coming in from other languages, saying that, okay, you forgot a case that's in this case situation. It'll list all the cases that it handles. Bottom line, type dispatch like this gives you the ability to really embrace the type system, and allows you to write very complex type checks that you could occur and write type actions. But type case especially does not give you compile time type dispatch. Okay, as far as I know, if you end up writing a type case and then compiling it, you will end up getting generic points. And I think the best way to illustrate this is, hold on, let me clear my REPL, is to disassemble one of the things that we just compiled. Right? Let's say recovered increment number. You could see immediately here, although we are passing in things of specific types, integers or floats, because it needs to handle both, it will actually jump those instructions, compare the type information here, as you can see on in this section of code, and based on that, it will call the appropriate generic plus operation. That's about as good as it's going to get in terms of it, because it has to preserve that type dispatching when it goes and executes the code. All right, it's still pretty fast. Question. So when would one use type case? Okay, so we have a question on when one would use type case. I think that's a very good question. I would argue that, especially when you're writing user interface macros, all right, things that are going to be happening at the runtime anyway, having type case and generic operations would be useful. Okay, think about a command line UI, where you could provide generic names for something, and then based on the types that are being passed in, you could dispatch behind the scenes to the appropriate function calls. Those are the places where I think type case becomes pretty useful. But if you're trying to use it for high performance code, forget about it, because it's not going to help you. Does that make sense? Type oh, thanks. So type declarations, really, when you're getting right down to it, you need to think about in what situation are you going to interact with the type system, okay? If you're doing what we're trying to do here, which is our final case here before I finish up, which is the generic add, where you could take the, and let's make it very, very simple. You might end up doing something stupid like, because here this is a little bit different just because of the fact that you have to kind of verify that everything is of a particular type first before you can actually do a generic add here. Honestly, one way of doing this, I don't think that this is the right way, but you can assume this and then you can write something like, say, car args, if it's of type integer. Okay, what we could do is we could first check to see if everything is an integer here, which is, again, I'm going to use a prog-n. You could do assert every integer p args. Okay, actually, let's do this correctly. Add cutter on that. Everything else is also, then you could just do reduce plus and args. And now what we've done is we've written a generic thing for that. And again, float. Let's do double. I don't believe you can write or in here, so if folks know how to write more complex type cases, let me know. And again, yeah, okay, cool. Assert every it looks like there's no type for P for double. Let's do that. And we do cutter args here, and then again, reduce is already, plus is already generic enough in here that I'm just doing this, but I'm again doing this for illustrative purposes. You may want to, say you can write this as saying for string. You might want to add this as saying that if these are all strings, then we may just want to concatenate them all. All right. I'm just going to go ahead and do end it here, and let me just do. I'm going to make this E-type case to make this a little easier for me. E, so I don't have to write all the cases. And two-style warning, undefined type double. What? Hold on. What was it? Single float, single. Yeah, let's say single float then. Although personally, I think that's maybe coarse. I'm gonna go look into that. That should not be the case. But actually, you know what? I don't even need to do this. We're going to just say that for a single float, we're going to say everything can be a number. All right. So now we have our generic add. Again, this is a really contrived example. You can use this just like our standard add function. You could do this 2.4, 5.6, 7, and it'll end up. Oops, hold on a second. I have to make this guy, because of the way I wrote the function. It's not treating that as a single precision float. It'll do the same thing. Obviously, in this case, as you just saw here, because of the way I wrote this function saying that the car of the arguments is going to actually go and determine that this itself is kind of flawed in terms of the example, in terms of the cases. It doesn't do an implicit conversion. Really, if you really want to make this more of a robust function, you would want to add checks to make sure that can we promote this guy to one of the other types in the same type definition. So could we convert this to a single float? Okay, if this is a convert to a single float, convert it to the appropriate float so that the cases can actually go and work through. There's some additional edge cases here, but I think the point is still very much illustrated here, and that is you can use this to write generic operations. But again, these are generic operations, okay, and they're generic operations on type information that's available at runtime, not at compile time. And so when it compiles it, it's going to compile what I showed you earlier, which is converting them into the lowest common denominator generic function call that can be invoked by the assembly, and it will go ahead and make that function call instead. And that's a big thing to be aware of, because there are performance implications on that. So profile your code, maybe figure out what your types are going to be, and then use declaim to actually go and determine whether or not. And declaim would be, well, use declaim essentially when you're creating your public API, just so that you provide some type safety guarantees when folks actually are using your APIs. You don't need it for prototyping phases, but it certainly helps because over time it will end up, in my opinion, providing people sort of a documentation as to what are valid and invalid inputs into your code, and they can use those accordingly. So that's it for my presentation on the type system. For more information on this, there's a lot of material out there on the type system in various forms. Of course, the Common Lisp cookbook is one of the resources I've been using. I also used Common Lisp recipes, which has some information on using types. There's also the hyperspec, which is probably the single source of truth on what the standard says about how to use types, and how to leverage a type system, and how to hint to the compiler to do certain things. There's also a couple of things in each of the individual Lisp implementations. So if there's a specific Lisp implementation that you're using, whether it be SBCL, or CCL, or ECL, or CLASP, they usually in their documentation have a section on types itself and handling of types. So look at your Lisp implementation documentation for more information on that. That's it for this week. Are there any questions? I'm looking at the live chat, so give me just a few seconds here. I appreciate for folks who are watching on the YouTube live stream. Before I let you all go, I'm glad that you guys are still here. There's a couple of announcements. But yes, folks who are on the chat, you can go ahead and jump in on the mic and ask questions.
Cool, so I'll jump in and ask a question. You're talking about declaim and these global declaration constructs and saying that they're for adding type safety. From what I can see in the hyperspec, with the type declaration. It looks like in every case where you would use something of the declared type and the actual use doesn't match the declared type, that you're in undefined behavior. So I'm wondering if you could explain in what way these constructs add type safety, or are they primarily just for like optimizations by the compiler?
So there are two ways. One is global declarations. Okay, as you saw in our example, what it did is it allows you to provide checks when you are running at runtime to see if there are type validations. All right. So if in the case of what you saw earlier when we were doing the hand number versus what the ftype provided in the declaim, in there the because the global declaration provided a more generalized type that was providing information to the inputs than what the locally defined declaration is providing in the case of declare. All right, because hand type, if you recall in the code here, let me just kind of for folks who need the context here, hand number is defined here as being an integer with something, and then we're saying that, oh, I'm going to take any integer that's going to be provided as being a valid input into add. This restriction is a type validation and says that at runtime, wait a second, these two don't match up. They're not in line. You're allowing a much larger number here, but you're saying that this is restriction. What the hell is going on? This is especially useful for prototype. When you're interactively prototyping and you're trying to determine what ranges of valid values are needed, and allows you to change your function signature and recompile accordingly. And because Lisp itself is allows you to do this interactively, right? It's not set in stone. Like when you're compiling, usually in a statically compiled language, what ends up happening is you end up having to do almost a large recompile of everything in order for you to actually get things to work. So that type safety that you're looking at in that case, in that context, is slightly different, okay? It's making sure that everything is aligned up before it does do code generation. Every time you compile a single function inside of a Lisp image, that's done for the most part, in isolation for everything else that's available inside of the Lisp image. It does not look at all the uses of this function to compile itself, all right? So the result of that is, and obviously this can hurt people too as well, if you change the function signature or make something more restrictive and stuff, and there's another function that's calling this guy, it may not necessarily, it may have made an assumption earlier on that's no longer valid based on the current signature, all right? So the type safety comes in only when you are certain that for your system when you're ready, and this is mainly for, again, like you hinted at, hints for the compiler to do certain optimizations. You've essentially restricted the API to saying that this is what it is going to be when you're compiling it. Does that make sense?
Yeah, I think that makes sense.
Yeah, just I've been burned by this before. I'll say this, where you have because as I've been playing around with the type system, especially, and this has been in recent days and recent weeks as I've been going through this a little bit more in detail. Especially global declarations versus local declarations. Knowing when to use what is very, very important. I would make the argument, and this is something that I wanted to kind of discuss with a much more larger audience, because I'm not an expert on this section, but I've gotten enough experience in it to have at least an opinion on it, and that is, I feel that in terms of API design, if you know at the API level, and when I'm saying for folks, when I say API level in the Lisp sense, I'm talking about if you treat all your functions as essentially symbols inside of a package, all right, a Common Lisp package that is being exported. Those exported symbols, those exported functions are your API. Okay, so when they load it into, when someone loads your library into their running Lisp image, they're going to get some global declarations that are happening just as part of the read phase. All right, and at that phase and at that point, you'd want to probably do some sort of declaims to make sure that your code gets optimized accordingly in your Lisp implementation's case. And if you know ahead of time that you want your API to be used in a particular way, having those F types there helps people, at the very least, look at your function signatures when they're using describe and determine what is valid and invalid, and then act accordingly in using it. So they don't actually accidentally get, oh, at runtime when they're interacting or playing around with their API, what we saw earlier with type case. Oh, this fell through this type case at this runtime. This is the invalid input, and it's probably knee deep in some piece of code that they wrote earlier on. But because they didn't actually go and say test out some bits and pieces as they were building their system, now they have to go and change a lot of code in order for they to account for a potential change in how you implemented something. So that's kind of what I was getting at. Like, declaim has its uses, but mixing declaim with declare is undefined behavior. That's a little bit of a mixed bag. I would argue that if you're using declare, stay with declare. But if you have an API that you're going to export to folks to use, having global declarations on those valid inputs would be useful for both you and for the users of your library. Any other questions? These keep them coming. Like, if there's something I'm not entirely sure about, I will go look it up and get back to you on it, just because I think it's important that we document some of these limitations about the APIs, and if there's some, or even how the type system works, and if there's corrections that we need to make as a community, I think having them at least on the record would make it a point for folks to actually take a look at it and see how we can improve things. Okay, guys. Well, I appreciate all you joining me, and I hope this provides some insight into the type system for folks as you guys are writing more and more Common Lisp code. Next time, I hope I'm still determining in terms of our schedule as to what next week is going to be provided. I'll provide a little bit more of an insight as to what's going to be going on there as the days come by. But before I let all of you go, I just wanted to mention a couple of announcements. There's where AFP has been is looking for talks for folks who are interested in giving a new talk, or we try to provide a talk every month. We've been kind of been lacking in terms of some of the virtual talks that have been happening along, just because there's so many of them. But I would, if there's a particular talk topic that you guys want to talk to, anything FP related, feel free to ping me on Functional Programming Slack. I'm Bugram on Functional Programming Slack. I'm also available on the Lisp Discord server if you guys want to talk about Lisp, and there's a Lisp library that you guys want to demo at Common Lisp Study Group. Please let me know. I'm more than happy to give the floor to anybody who wants to demo some cool stuff in Common Lisp. Additionally, Common Lisp has now been expanding and has been reaching out to other meetups, and I'd like to highlight a couple of new meetups that I've been going to that are that I've been going to that I want that I think people should start looking into, because now everything is virtual. It's very, very useful to like check out the national meetups that are around. One of them is actually the Tucson Functional Programmers meetup. It's hosted actually by one of our attendees, Michael White. Michael, if you have a chance, could you just go ahead and post the actual meetup URL? I'll go ahead and post that on the live stream as well. And then and as well as folks who haven't heard about it, there is also Lisp Nick, and that's Lisp NYC. That is a meetup that is also kind of a sister meetup, if not the OG in terms of Lisp meetups that are around. It's a really good meetup that I think that folks should check out as well. So one more announcement, and that is this is just a pre-announcement. We are going to be having a talk on PureScript in the coming weeks. So for folks who are interested in PureScript, which is a Haskell-like language for web development, feel free to stay on the lookout for announcements in the functional programming meetup list. If you are not one of our members already, I encourage you to go to meetup.com and register so that you can get announcements and as well as talks that we're going to be going to. So there's no other questions. I will call it, and I will post the Lisp Discord server and Slack URLs as part of the YouTube description links. So for folks who are interested in giving us talks or providing feedback, to ping me on there. So I'll see you guys next week. Thanks for joining.